So have you ever actually stopped to think about how your most private digital data stays secure when it's just out there flying across the internet? I mean, it doesn't just happen by magic, right? Your information is actually being protected by this incredible, invisible mathematical assembly line. Welcome to this explainer. Today we're going to take a VIP tour of that exact assembly line. We're demystifying the Advanced Encryption Standard, or AES. We're going to break down exactly how this powerhouse of an algorithm takes your perfectly readable data and basically transforms it into an absolute unreadable vault.
Okay, to make this whole complex process super easy to grasp, we've broken our factory tour down into 4 simple sections. First, we'll meet the new standard. Second, we'll check out the 128-bit assembly line. Third, we'll dive into the transformation rounds. And finally, we'll wrap up with keys, sizes, and variations.
All right, let's jump right into Section 1. Meet the new standard, and why we had to retire DES for a modern world.
You see, for a really long time, the whole world relied on something called DES, the Data Encryption Standard. But, well, as computers got faster and faster, DES actually became dangerously vulnerable. Its 64-bit input block size was honestly just way too small to withstand modern cyber attacks. We desperately needed a heavier vault. Enter AES. Published by NIST back in 2001, it was this powerful, secure alternative that significantly upgraded our baseline security, literally doubling the raw intake size from 64 to 128 bits.
But before we officially step onto the factory floor, let's just make sure we're on the same page about what kind of machine AES actually is. Cryptographers call AES a symmetric block cipher. So what does that actually mean for us? Well, symmetric simply means that the exact same key is used to lock the data during encryption and to unlock it during decryption. It's kind of like having just one single physical key to the front door of your house. And block cipher. That just means AES doesn't waste its time processing your data one tiny bit or one single byte at a time. Instead, it scoops up a fixed-size group of bits, a block, and processes the whole shebang all together at once.
Moving right along to Section 2, the 12-bit assembly line. Welcome to the factory floor.
On this specific factory floor, there is one magic number that absolutely rules the entire intake process, and that number is 128. AES takes in exactly 128 bits of your raw input, what we call plain text, at a time. Now, since 1 byte is equal to 8 bits, if we do a little quick math, 128 bits comes out to exactly 16 bytes. This 16-byte chunk, that is the raw material our mathematical assembly line is about to process.
But AES doesn't just, dump those 16 bytes in a straight line on the conveyor belt. No, it's way more organized than that. It arranges them into a neat 4x4 grid called the state array. 4 rows, 4 columns, perfectly holding our 16 bytes of data. You can think of this array as the literal conveyor belt basket that's going to carry your data through the entire encryption process.
So what's the actual roadmap here? Well, here's the high-level life cycle of your data. Step 1, your plain text gets loaded right into our state array basket. Step 2, it goes through an initial transformation, just to jumpstart the whole process. Step 3, the data travels through a series of standard processing stations, which are called rounds. Now, the total number of these rounds can vary, so we just represent that mathematically with the letter n. And finally, Step 4, the data hits the final round, which actually behaves just a little bit differently to fully seal the vault.
Which perfectly sets up Section 3, the transformation rounds. Let's see how this data is actually processed. Okay, so inside every single standard round, your data undergoes 4 rapid-fire mathematical transformations. It goes like this: substitute bytes, ShiftRows, MixColumns, and AddRoundKey. Round 1 blasts through these 4 steps, then instantly passes the array over to round 2. Round 2 does the exact same thing, passing it to round 3, and so on. It's just a brisk, relentless, highly mechanical loop.
But wait, there is a really vital exception to this loop. That very last station on the assembly line actually drops one of the steps. It features only 3 transformations instead of 4. So, say your factory is set up for 10 rounds. Rounds 1 through 9 are going to execute all 4 steps, but round 10, it only executes 3. And believe it or not, this precise little bit of asymmetry is absolutely critical to the security of AES. Now, you might be wondering, how do these processing stations actually do the work? Well, they don't operate on their own. They need tools. Specifically, every single round requires its own unique key to process the data. This means for that very first step, the initial transformation, we need a round 0 key. For round 1, we need a round 1 key all the way down the line to a round N key for the final station. And here's the kicker. All of these round keys have to be exactly 16 bytes or 128 bits in size. So where on earth do all these different keys come from? They're dynamically generated on the fly by a key scheduling algorithm that builds everything out from your one single original input key.
And that brings us to our final stop, Section 4, Keys, Sizes, and Variations. It's time to meet the factory manager.
Throughout this explainer, you might have noticed we've been using the letter N to describe the total number of processing rounds. We haven't just given you a static number, like 10 or 12. And there's a reason for that. The number of rounds in AES is entirely variable. So what actually tells the factory how much work to do? What's the boss? The answer is the size of the original input key.
See, AES actually comes in 3 distinct flavors, all based on the manager's key size: AES 128, AES 192, and AES 256. If you use a 128-bit key, it means your data is going to face 10 rounds of processing. Bump that key up to 192 bits, and the factory extends the line to 12 rounds. And if you go all out and use a massive 256-bit key, your data goes to a staggering 14 rounds. To put that into perspective for you, cracking an AES 256 key with current computing technology would literally take billions of years. The bigger the key, the more rigorous the mathematical processing.
All right, let's step back and summarize what we've learned about this incredible machine by looking at what stays constant versus what changes. No matter which version of AES you are using, the raw material size is completely constant. It always takes in a 128-bit plain text block, it always spits out a 128-bit Cipher text block, and every individual processing station is always going to use a 128-bit round key. But the variable, the thing that dictates the entire workload, that's the size of your original starting key, which decides if your data gets 10, 12, or 14 rounds of rigorous mathematical transformation.
And after all of that, after moving through the input state array, the initial transformation, all those relentless standard rounds of substituting, shifting, mixing, and adding, and then surviving that specialized final round, boom, the data rolls off the assembly line. The final output is 128-bit ciphertext. It has been completely transformed. It is exactly the same size as the raw material that entered, 16 bytes, but it is utterly unrecognizable. It's been scrambled into a mathematically perfect vault.
As our source material brilliantly sums it up, because of its many powerful features, AES is widely used even in today's world. I mean, really think about that the next time you send a secure text, log into your banking app, or just buy something online. Right at this very second, this invisible 128-bit assembly line is churning away in the background, flawlessly guarding your private life. It kind of makes you wonder, doesn't it? What other invisible mathematical machines are running the modern world right under our noses? Thanks so much for joining me on this explainer, and hey, keep your curiosity sharp out there.